Hello everyone, the talk will be in English. So during this talk, what we want is to assess the security of an artificial intelligence, and the special focus here is that we'll be focused on how can we assess the security of an embedded artificial intelligence with physical attacks. But first, just an introduction, who I am. So I'm working in Thales, in the Thales group, and in Thales there is a lot of division, so from space to digital security. And me, I'm working in the defense and security unit, and in particular, I'm working in a center of expertise where I've been involved in a security lab, which is called as an ITSEF. ITSEF for Information Technology Security Evaluation Facility, or in French, an ITSEF is known as a CESTI, for Centre d'Évaluation. And our main goal in this kind of security lab is to assess the security of device in order to improve the security of our suppliers. We are based in Toulouse, in south of France, and we are specialized in the attacks, hardware attacks and software attacks on embedded systems. So once we introduced why I decided to target an artificial intelligence, we can question why should we assess the security of such kind of solution. So we have to being prepared to assess the security of artificial intelligence because in the next few years, the suppliers, the developers must be able to provide secure AI. Why? Because of the Artificial Intelligence Act. But first, what is AI Act? So the AI Act is a regulation report, regulation methodology that will be used by future suppliers in order to being confident in the security of artificial intelligence. So in other words, the developers must be compliant with the AI Act in order to being sure that their solutions are able to be secure against different cyber threats. But to identify what kind of compliancy we have to respect, there is some risk that must be specified from the minimal risk to the unacceptable one, and depending on the risk, there is some compliancy that must be respected by the developers. So first, for the minimal risks, here we talk about mainly for example, artificial intelligence used in video games, and here Europe will no provide any restriction on such kind of solution. So in other words, for the developers, if some minimal risk AI are developed in systems, therefore no restriction will be mandatory for putting the system on the market. Then, for the low risk solution, here, for example, the chatbot, the deepfake for artistic purposes, the suppliers as well as the developers must provide a clear description of the solution, of the AI solution to the users in order to clearly understand for which purpose the AI has been released. For the high-risk system, here we talk mainly about for example, real-time biometric identification, and I will briefly describe you all the requirements in the next slide. But before that, the last risk that must be considered is the unacceptable one. So for example, the artificial intelligence systems that are designed to manipulate people through subliminal techniques. And here, such kind of unacceptable risk AI will be banned by the Europe. And so the developers that want to sell this kind of solution in the market cannot because of the AI Act. But if we take a brief look on the high-risk system, what we can observe is that some requirements must be respected in order to be compliant with the Europe requirements. The first one is that all the training dataset, the validation dataset, as well as the test dataset, must be of high quality in order to reduce as much as possible the bias induced in an artificial intelligence. Then, all the technical details must be provided to the users in order to respect the transparency of the AI. Then, obviously, because if we use AI in high-risk system, we have to provide AI risk management in order to reduce as much as possible the cyber threats and find the suitable defenses, the suitable countermeasures, depending on the attack path that can be identified. And finally, obviously, we have to develop, or the developer have to develop solutions that are resilient to cyber attacks. And from my point of view, so from a security lab point of view, the evaluation of artificial intelligence are really important because they have to be resilient to cyber attacks. And that's why we are currently working on this kind of subject. And that's why we are trying to identify solution and different kind of attack paths against artificial intelligence. So just some key dates in order to provide you a concrete overview of this AI Act. In May 2024, the AI Act will be officially published. Then, in November 2024, all the systems that are considered with an unacceptable risk will be banned on the market. Then, in May 2025, all the generative models, such as the large language models, must be complied with the regulation, so with the AI Act. And finally, in May 2026, all the systems must be compliant with the requirements provided by the Europe. So in other words, as an ITSF, as a security lab, we have to be prepared before May 2026 to assess the security of such kind of solution, because we have to provide a clear security assessment of those systems against different kind of threats. So we have to develop our expertise in the security assessment of these systems. But when we talk about attacks against AI system, what exactly we can describe? So first, what I want to introduce you is 4 attack areas that has been extracted from a NIST document, which is the NIST Trustworthy and Responsible AI that has been released in January 2024. And first, in such kind of, in this document, the first attack that has been proposed is what we call the evasion attack. And the goal of this kind of attack consists in fooling the decision-making process of the artificial intelligence, or for example, the neural network. So to do so, we can construct, for example, adversarial example. And here, on the right part of this slide, you have a short video where on the left part, you have the classifier input, where you can see a banana, and on the right part, the classifier output. So when we have a banana, therefore the classifier correctly predicts a banana, but here, as you can see, we had some noise on the input, and then because of this noise, the banana is no more predicted as banana, but here as a toaster. We will see a concrete example of adversarial example in a few minutes, but just to give you a quick overview of what it is, we just have to add some noise on an input in order to fool the decision-making process of the artificial intelligence. So for example, if we use this kind of attacks in a high-risk system, for example, biometric system, we can maybe find some solution in order to bypass the security application behind the biometric system. Then, the second attack we can consider is what we call data and model privacy. Here what we want is to retrieve and reveal information on confidential data or on the neural network itself. So for example, we can conduct what we call a model extraction attack. Here, what we want is to retrieve the neural network architecture, the weights of the neural network, the activation function, and so on, such that if we are able to conduct such kind of attack scenario, therefore, we can copy a device that can be protected with IP for intellectual property. Another attack is what we call data and model poisoning, and here what we want, again, is to fool the training process of a neural network in order to bias its prediction, or to conduct some denial of service attack. And the last one I would like to introduce you is what we call abuse attack. And here, in this kind of attack, we want to target a generative model in order to, for example, generate malware with LLM, a large language model. And a concrete example is what we call the prompt injection attack. So the goal of this attack consists in interacting with, for example, a chatbot. On the left side of the slide, you have a website, which is the prompting.ai website. And here, this is just a challenge where we want to get a flag or a password from a chatbot. And the goal here consists in interacting with the chatbot in order to get some sensitive information, here a password. So as you can see on the top, I just asked the system, the chatbot, to give me the password, and obviously it just provides me the information I want. So this is the first level. I encourage you to reach the other one in order to get a concrete overview of what such kind of prompt injection attack can do. But here in this talk, we will mainly focus on the evasion attack, and we will see how we can conduct adversarial example without any prior knowledge on the artificial intelligence. But first, we can question what adversarial examples are. So obviously, I already briefly introduced what such kind of example can do on the artificial intelligence. But just a brief recap. Here, let's assume that we train a neural network to recognize a figure included in an image. So on the image you can see here is an image extracted from the MNIST dataset, which is a widely known dataset in the machine learning community. So we train our neural network such that the prediction provided by the neural network from this input is, we hope, a 7. So we send our image to our neural network, and once the image is processed by our model, we have the prediction, and here, okay, it's good, we have our 7. So the neural network is correctly trained with, in the purpose of predicting a figure. But what we can do from an adversary's point of view is that we can generate adversarial example, such that this kind of example, the goal consists in inserting some noise into the input, such that this noise cannot be seen by our own eyes, but here, just for the demonstration, I decided to add a huge amount of noise in order to clearly visualize the differences between the original input from the evil one. But what we wanted is added some noise on our input, such that if this noisy image is sent to our artificial intelligence, then the prediction will be fooled. So in other words, if you try to translate this example into high sensitive area, for example, the biometric case, we can maybe easily bypass a security function in order to fool the biometric system. But unfortunately, in practice, generating such kind of solution, such kind of adversarial example can be difficult because there is two kinds of solution. The first one is what we call the white box scenario. So here in the white box scenario, we have a full knowledge on the neural network, its architecture, its weights, its activation function, and so on, such that based on those information, we're able to clearly understand the decision-making process of the artificial intelligence, and then find how we can add our noise in our input in order to fool the decision-making process. But on the other hand, we also have the black box scenario. In this context, we have only a partial knowledge on the AI system, and in particular, we only know what we call the logits. So a brief recap of what the logits are. So in a neural network, you have the succession of nonlinear layers, and at the end of those linear layers, we obtain a score that we also call the logits, and those scores are unfortunately not defined as a probability vector. So to transform those scores into probabilities, we use what we call a softmax function, and then once this softmax function is performed, we obtain the probability of observing each class of the for which the neural network has been trained. So here, for example, what we want is to retrieve a figure in an input. So we have 10 classes from 0 to 9. So the logits here characterize the confidence in the neural network to predict each of those figures. But as you can see here, in a real case scenario, this partial information cannot be obtained by an adversary. So the practical issue is how can we generate adversarial example without any knowledge on the device? So in other words, how can we generate adversarial example without any knowledge on the logits? To do so, we proposed a new kind of attack that combines physical attacks and software attack, such that first, the goal of the physical attack consists in using side-channel attacks in order to extract the logits from an embedded device that implements artificial intelligence. And then, once this first phase is conducted, therefore the adversary has the access of the logits, so he can conduct state-of-the-art adversarial attacks, such as, for example, the zoo framework that we used. So zoo is for zeros order optimization. So it's just an optimization problem that can be performed in order to generate an adversarial example. So our attack is decomposed in two phases: extracted the logit with side-chain attacks, and then generate the adversarial examples. But concretely, how can we conduct this specific scenario? So to conduct this attack, we need three components. The first one is obviously a personal computer in order to interact with the embedded system. And then we use an oscilloscope in order to conduct our side-channel attack. But before that, maybe for those that are not aware of what side-channel attacks are, the goal of this kind of attack consists in analyzing the physical properties of a system. For example, its power consumption, its electromagnetic emanation, such that based on those information, we want to correlate the sensitive data with the physical signal. And once this correlation is conducted, we are able to retrieve the sensitive information from our physical traces. Just for your information, historically, this kind of attack has been introduced for targeting cryptographic implementations. And here we just move the paradigm into the artificial intelligence field. So, okay. First, what we want is to conduct our side-chain attack to extract the logits. So to do so, we send our input to our neural network, such that during the decision-making process, we capture the related physical trace, here an electromagnetic trace. And once this physical trace is obtained, the adversary will acquire it using some statistical tools in order to retrieve the logits. And then, once those logits are extracted, so once the first phase is conducted, the adversary will use the zoo tool in order to generate the adversarial example, and then send this adversarial example to the neural network in order to fuel the decision-making process. So here we use the side-chain attacks in order to retrieve the logits, and so in order to conduct an attack in a full black box scenario. So we have any prior knowledge on the AI. So let's try to get deeper into the first phase, so the extraction of the logits. So during our experiment, during our work, we implement an artificial intelligence into this device, which is a ST microcontroller. So this device can be built on the market easily. And in this device, we embedded a state-of-the-art neural network, which is known as DanceNet, and we decided to quantize it in order to implement the neural network into the device. Because if the neural network is too large, it can be difficult to implement it into an embedded system, so we have to use some quantization technique in order to implement the device, implement the artificial intelligence, the neural network, into our device. As I mentioned earlier, here we want to train our neural network for the MNIST dataset. So we want to generate a neural network that can predict a figure from an image, such that the figure goes from 0 to 9. So we have 10 classes. And to capture the physical property of our embedded system, we use an RM probe. The RM probe, yeah, perfect. The RM probe can be seen here, and thanks to this RM probe, we capture the signal that is emitted from the device, and inside this microcontroller, we have our neural network. So this is exactly how we can extract, or how we can set up our experiment. So once we set up our experiment, we have to clearly understand how does a neural network works. So maybe just a brief recap of how a neural network works. So first, let's assume that we have an input that we want to provide to an artificial intelligence. So as I mentioned earlier multiple of times, during the decision-making process, we want to extract the sensitive information. But if we take a look inside this part, what we can see is that we design a neural network. And as I mentioned earlier, this neural network is no more than a consecutive set of nonlinear layers. And at the end of this neural network, we obtain confidence scores, also known as logits. And unfortunately, those logits are not transformed into probability vector. So to do this transformation, we use the softmax function, and then we obtain our probability. And this probability is related to each class of the neural network. So to correlate, so what we want now is to understand how we can correlate the physical traces with the given neural network, and how we can correlate the logits that we want to extract with the given neural network. So to do so, we have to clearly understand when the logits, or where the logits are manipulated inside the neural network. Because to generate a correlation between physical signal and sensitive data, the sensitive data must be manipulated by the device. And here on this slide, the only function that manipulates the logits is the softmax. So what we want here is to target the softmax function, or get the physical emanation of the softmax function in order to retrieve information on the logits. But here we take a brief look at the softmax function. What we observed is that the following C code is implemented, briefly. So this C code requires a vector named vecin. This vector is a vector of dimension 10, such that each element of this vector is characterized by the logits associated with each class, so L0 from L9. Then we have a base value that will capture the maximum value into vecin. So to do so, first the base value is initiated to 0. Then we will compare this base value with L0. Here we assume that L0 is higher than 0, so the base value will be L0. And we conduct this comparison with the base value through all the vector elements. So with L1, L2, L3, L4, here we assume that L4 is higher than L0, L5, L6, L7, we assume that L7 is higher than L4, and so on. So that at the end of this process, the base value will be equal to L7, and all the logits will be manipulated by the device. But if we want to clearly correlate so we are pretty confident that the device manipulates the logits, but if we want to being 100% confident that all those logits are manipulated, we have to take a look at the assembly code of, for example, this if condition. On the right part on this slide, you have the assembly code of the if condition, and what we can observe here is that this line and this line load two values. The first line, so the line 5, load the if element of the vec_in, so of our vector. So it loads the if logit. And the line 7 will load the base value. So through those loading processes, we're able to being confident that the logits will be manipulated by the device. And that's why we can conduct, and that's why we can extract the sensitive information, so the logits, from the physical traces. It's because the neural network will manipulate the logits. So once we understand how the softmax function is implemented, we can acquire our side channel or physical traces. So to do so, we need an RM probe and an oscilloscope, and then we can send our input to the neural network in order to acquire the related electromagnetic emanations. And because the adversary can send as many images he wants to the artificial intelligence, obviously he or she can acquire as many physical traces he or she wants. And from those physical traces, we want to use some statistical tools in order to extract the sensitive information. So to do so, the adversary will use some statistical tools. I will not describe them, but just for your information, those statistical tools are known as template attacks or logistic regression. And one fun fact here is that we can use deep learning techniques in order to treat or to process our physical traces. So in other words, we can use deep learning techniques to extract the logits that has been manipulated by an artificial intelligence. So in other words, we can use deep learning mechanism or deep learning solution to attack AI. Once this first phase is conducted, therefore, we can extract the logits and we can we can conduct our second phase, which consists in extracting or generating an adversarial example from those logits. So this is a recap of our first phase. So we have our input, we send our input to the AI, we acquire the physical signal, and we will treat it. But what I didn't mention earlier is that in a real case scenario, one physical trace is not enough to extract all the logits values. So to do so, we will acquire multiple traces with the same image, with the same input, in order to reduce as much as possible the environmental noise that can be captured by our probe, and so ease the extraction of the logits. So we send our input to our artificial intelligence a second time, get a new signal, a new physical trace, and then we conduct this experiment here 3 more times. And then from those 5 physical traces, we use the statistical methods such as template attack, logistic regression, or deep learning techniques in order to extract the logits. And from those logits, then we can use the ZO algorithm, the ZO method, in order to generate our adversarial examples. So just a brief introduction of ZO. Here you have the optimization problem that is proposed by ZO. Just briefly, what we want is to generate an adversarial example X stars from an original input X. And to do so, this term wants to minimize the distance between the original image, so X, and the generated one, X stars. So during the optimization process, what we want is to construct an image that is as similar as the original one. And then this term is beneficial to force the neural network to predict a given class. So if I want to generate an adversarial example to predict a tree or whatever I want, I can suggest this term to the optimization problem, such that what we want is to generate an adversarial example that is as similar to the original one, and such that the predicted class, so here a tree, is the most probable classes for the neural network. So this equation is just that. So once we have those information, once we have those logits, we can solve our optimization problem in order to generate an adversarial example and send this adversarial example to our artificial intelligence. And here, what we observe is that we obtain a tree. Now, what I want to propose you is just a short demonstration. So here on the stage, yes, I don't need that. So, sorry. Allô, allô. Allô, allô. Okay. So here we have the exact setup we consider in our experiment. We have our computer, our embedded system where we implemented a neural network. So here our neural network is trained to make a prediction on civil and military vehicles. And then we use an OM probe here that we connect to an oscilloscope. And we will capture the related signal in our computer, and then we will trade it in order to retrieve our logits. Oh. Okay. So the goal of my, so first I have to connect my computer to the neural network in order to communicate with it. And one really important point here is that we have to position the sum with slight precision, because if the probe is not correctly positioned on the device, therefore we cannot capture the signal that is interested to extract the logits we want. So sorry for the delay, but I have a graphical interface to communicate with the neural network. If I found it, yeah. And what I want to show you is that here in blue you have the current signal captured by the neural network. So as you can see here, this is just the environmental noise. And if I ask the artificial intelligence to predict an image, then you'll see that the signal here in blue will be modified. And this modification ensured us that the signal that is captured will be correlated, as I mentioned to you earlier. This suggests that the electromagnetic emanation signal is correlated to the prediction process. So I initiated the artificial intelligence. And then here, So maybe you can see it, maybe not, I don't know. I hope. But here on my screen, you can see a tank that we will send to the neural network. Okay, and as you can see, here we do not observe any modification on the signal. So what does mean? It means that my probe is not correctly located on the system. So I just have to move it a little bit, and then maybe we can observe a signal that is directly correlated with the decision-making process. Okay, we'll try again. So this concrete example shows you that finally conducting a sidechain attack is really difficult in practice, because if we do not have any information on the device, therefore finding the suitable position can be really difficult. The proposition can be really difficult. No. Okay. We'll try again. And yeah, here you see a concrete difference between this signal, sorry, and this one. Yeah, here. And this shows you that the current electromagnetic, the current consumption of the device is directly correlated to the decision-making process. And from this signal, we will use, for example, as I mentioned earlier, some deep learning techniques in order to extract the sensitivity for the logits from this signal. As you can see here, for our own eyes, we are not able to clearly identify the value of the logits from this signal. But if we use some statistical tools, if we use some methods that clearly retrieve the interesting features in the physical trace, therefore we will be able to retrieve our logits and then generate adversarial example that fool the decision-making process. So yeah, I conclude my talk. If you have any question, do not hesitate to ask. And yeah, thank you very much for your attention. Oui. Je ne sais pas s'il y a un micro qui est prévu.
So thank you for your presentation. Do you know the number of logits, or do you discover them through side channel?
So there is multiple kind of attack that can be conducted in order to extract those logits. Here in our experiment, we didn't know the logits, so we just use the sidechain attack to extract them. But depending on the context, we can also consider black box scenario or white box scenario in sidechain paradigm. And if you are in a white box scenario, you can consider that you have a copy of the device, and from this copy, you can know, for example, the logits. But here in this context, we didn't know any logits. And so we just use the sidechain attacks to extract them.
I mean, the number of logits. Here we know it's maybe one or two because it's a yes or no. But in an image classification AI, we don't know the number of classification.
Okay. So with the sidechain attacks, depending on the implementation, so for example, if it's on a microcontroller, all the operations are mainly sequential. So we are able to clearly identify a pattern dedicated to the manipulation of a logits, and then just we have to count the number of patterns and identify the number of logits. And here, this is not exactly what we conducted because we already trained our neural network, so we know that the number of logits will be 10 because we have 10 classes. But in real case scenario, yeah, we can conduct our hypothesis on the number of logits like that.
Thank you.
Autre question?
Hello.
Hello.
Thank you for your presentation. I was wondering, do you have like some kind of robot to, like the detection phase of the side channel, I would call it? Like I was thinking maybe of an array where you test different positions. Did you automate that?
So in practice, the best way is to manually identify the RM probe, because obviously you can use maybe AI methods in order to identify the best solution, the best RM probe. But what we wanted here is to identify the AM position that provides us the best liquids. So in other words, the best signal. But as we didn't know exactly what kind of signal we need to recover our logits, it's really difficult to identify a robot that can discover this kind of behavior for us. So because we mainly know the exact algorithm that is implemented, for example, if in cryptography, if there is an AES or a RSA, we already know exactly what kind of behavior we expect. So we just have to use our hand to clearly identify the AM position, because it's faster than using automatic tools. But if we don't know any behavior we expect, we also use the manual techniques because it's the best one. But obviously there is also some automatic tool, but in an evaluation process, we never use it.
Okay, thank you.
Hi.
Hi.
Is it possible to find a modification which is powerful enough so every input will be corrupted? Or do you have to calculate a new modification for every input of the network?
It really depends on the state-of-the-art result in the machine learning community. And here, the tool we used require to modify each input. So if we need to generate, I don't know, 100 adversarial examples with different images, we have to resolve the optimization problem for all those images.
So for the moment, it's not possible to create, for example, a stickers where you put on the front of the tank and it's Clio for the AI?
Honestly, I don't think so yet.
Okay, thank you.
I have a question from the Twitch chat. They asked it earlier. They were asking, what is the minimum number of pixels that need to be altered on average for the attack to happen or succeed?
So for the first phase, so the side channel phases, it's totally independent on the number of pixels. So it's the side channel attacks is only dependent on the number of logits, but not on the dimension of our input. However, the second phase, so the generation of adversarial example, can be impacted by the number of pixels, so the dimension of the input. And once again, it depends on the tool we used. For example, in our use case, we used 32 by 32 images and 224 by 224 by 3 images in order to conduct our attack. But maybe if we use HD images, it's just it took a little bit more time, but it is just a time-consuming question. From an attacker point of view, the number of pixels doesn't matter.
Okay, thank you. I have another one. Sorry if I don't pronounce it right. Is there a difference on the oscilloscope if we use another type of format, for example, tensor RT and O and X or others?
So about the oscilloscope?
Yeah.
So
If we see difference on it.
I don't think so. The most important part on the oscilloscope is about the number of bytes that characterize our resolution. For example, if we use oscilloscope with 8 bits, we're able to conduct our attack. If we use oscilloscope with 12 bits, 16 bits, therefore we are also able to conduct our attack, whatever the brand of the oscilloscope. But if we use, I don't know, oscilloscope with 4 bits, I don't know if such kind of oscilloscope exists, but maybe it can be problematic.
Okay, thank you.